Okay, we're going to start. So, you're moving on to chapter 10, 10.1. We're talk about parametric. Well, I think. Just talk about both at the same time. Parametric curves. Calculus. Meaning how to find derivatives, integrals, limits. So this is just a function of x and y. It says x's and y's mixed together, so this could include something like y equals x squared, a typical kind of function, or something like x squared plus y squared equals 4, or something similar to that. Any expression that you're used to seeing. Sometimes we would have the desire, sometimes out of sheer necessity for solving a problem, sometimes out of some sort of preference, of instead of looking at this curve as some function of x and y where x is doing something and y is responding, right? There's an independent variable and then there's a dependent variable. Sometimes you want to isolate each variable and on their own think of them as functions of some other variable, like you're trying to find function that govern each of these individuals. Okay? Sometimes we like to find rules that govern each variable individually. If we find equations, so if we find equations, yeah, let's see. So let's say there's another variable that I'm expressing the x-coordinate as a function of t. Right? T is usually used because it's usually referring to some point in time that we care about, and y as a function of t. So I'm not thinking of these guys as this is the independent variable for that guy. I'm thinking of individually as individuals, these guys are their own functions, and I can come up with rules that govern what each one is doing. We say we've made what's called parametric equations. Right, so it's basically when we want to isolate each variable individually and talk about them in their own right. And the set of equations x equals x of t, y equals y of t is called a parametric curve. You might also say, we can also say, when going from the xy expression to the parametric expression, that we parameterize the curve. That's the expression we use. And by the way, y, the new variable, t, is called a parameter. Now in multivariable calculus, this is usually you get a lot more complicated because you can express, you'd have sometimes a z variable and more variables, and they can be expressed in terms of multiple variables, and these all have meanings. But we're in Calc 2, we're doing still single variable calculus, so we're just expressing x and y as functions of one other variable. Right? There are many more ways you can go about this, but in Calc 2, that's where we stop. Right? So we're given some expression in terms of x and y, but for some reason, right, and we'll see some uses for that in like 10.4, we want to think of each variable individually as functions in their own right of some other independent variable. So I created a new independent variable called t, and I'm describing what x does in terms of t. And then I describe what y does in terms of t. So these equations are called parametric equations, and then when I consider them together, that's called a parametric curve because it will be the same relationship as before, and I'd be able to graph it. So I can get a curve, and to go from this to that, I say I parameterize this curve. So I can say parameterize y equals x squared. It means you need to write a set of equations here that describe that curve in terms of some other variable. Right? And this variable, this new variable that you invented, is called the parameter. Okay? So that's basically what a parametric curve is. So let's do some examples so you can see what I'm talking about. First one, we're going to start very simply, and then move on to more. But we're not going to get too complicated here anyway. It's just a very new idea that we're introducing. So, example. Sketch the parametric curve. So let's say I gave you a curve, x equal 2t plus 1, y equals t squared. So this is a curve in which the x-coordinate is behaving like this line, while simultaneously the y-coordinate is behaving like that parabola. A. By plotting points, B. By eliminating the parabola. Very usually, plotting points, like, I mean, we're in Calc 2, plotting points is sort of beneath us, I understand. Maybe let's do B first. Right? Now, eliminating the parameter means unparameterizing the curve. Let's eliminate the t from consideration and try to get back to x and y. Sometimes we can do this, sometimes we cannot, sometimes we don't want to do this, but in this case we can, and I'd like us to try to see what kind of curve is that talking about. How do you think you can go about that? How would you eliminate the parameter? Get the t out of. Yeah?
You could do t equals the square root of y, and then put the square root of y in for t in the x function.
Exactly, right? One way is you can solve for t in both sides. A little hiccup with what you said is that if I square root this, I'd have to consider plus and minus.
Okay, yeah.
Right, I'd have to do two individuals with ones. So what I'd probably do is solve for t in one of them and plug it into the other one. Usually the one that gives me the least options to worry about. So I don't want to deal with the plus or minus. I'll probably go with this one first. And so the method here you can use is substitution. Solve for t in one, plug it into the other. alternatively, can solve for t in both and then set the expressions equal to each other. So what you would do depends on the situation. Like I said, here, one reason why I wouldn't want to solve for t in both is because here I have to deal with a plus or minus. So if it were t cubed, that would be a different story. I might have done the second method. So here what I would say is since x is equal to 2t plus 1, this means if I solve for t, I would get t is equal to x minus 1 over 2. And then what I would do is plug into y. And so this would be, my y is now, instead of t, I can plug in this. And so my y is just going to be x minus 1 squared over 4. And of course from that I can realize that what this thing was describing to me was just a parabola. A parabola shifted to 1. Right, and of course when x equals 0, this guy hits a quarter. Right, so this same parabola here, I could have expressed in this way. Note, parameterizations are not unique. There are multiple ways to parameterize any curve. So for example, you can always do sort of a kind of cop-out. If your y equals x minus 1 squared over 4 could be parameterized by just kind of slightly letting x be itself, like let it be the parameter, and then set your y is equal to t minus 1 squared over 4. That would give you exactly the same curve, right? And it's just a parametric sets of equations. But there are multiple ways to parameterize anything, but given that something is parametric, you should be able to find or sketch something else. And usually there are certain patterns here. So if you see x and y are both linear equations in t, then odds are this is just a straight line. Well, that it would have to be a straight line. Right? If one of them is linear and the other one is parabolic, then it's going to always be a parabola. And you sort of have to be careful though, because you might have only one side of the parabola if they both have to be positive. Another common thing is also very common. Is the idea of circles. Now we spoke about what sine and cosine are, that they really parameterize the circle. In fact, that's exactly how you can think of sine and cosine in this new language. They're really functions that parameterize the circle. Okay? So we were talking about when we spoke about the unit circle, for example. We spoke about the fact that given this angle here, we define the cosine to be such that the cosine of the angle gives you the x-coordinate and the sine of the angle gives you the y-coordinate. If you realize what you were doing, you are saying x is equal to cosine of theta and y equals sine of theta. In other words, you're creating a parameter that you call theta, and you're writing x and your y in terms of this parameter. And by doing that, gave birth to all of trig. And that allows you to solve lots of problems. And so one use of parametric equation is sort of exactly that. by just defining your variables to behave certain ways that are convenient, you can derive a lot of other things from that idea that can be very useful in many contexts. And so the idea of using sine and cosine to parameterize circles is very common. In fact, if your circle, instead of not being the unit circle, if your circle had radius r and theta, then you can, by SOHCAHTOA, you can derive the fact that your x would be r cosine theta, and your y would be r sine theta. And you can parameterize that, where r is a constant and it's the radius of the circle. You can also notice then that, let's say you were given this, you could always go back to the original equation, which we know, by the way, the equation of this is x squared plus y squared equals r squared. You can always go back to the equation by, once you see sine and cosine, you try to create the Pythagorean identity. So you kind of want to square the cosine and square the sine term. You'd realize that this is r squared times cosine squared plus sine squared. That would give you 1, and that gives you r squared. So you get that x squared plus y squared equals r squared is the curve that is described by this. In a similar way, I can generalize this to be centered at any point. We can also change the center if we wanted. So for example, to parameterize. Let's say I have a general circle, x minus h squared plus y minus k squared equals r squared. How could I write that as a set of parametric equations? Well, because I know how cosine and sine work, how they were defined, I can let this entire inside here be the cosine, and this entire inside here be the sine. R, to get that r squared. And so what I would get is I would have x minus h is equal to r cosine theta, and y minus k is equal to r sine theta. This means I can set x is equal to h plus r cosine theta, and y is equal to k plus r sine theta. And if I restrict theta to 0 and pi over 2, this parameterizes the circle. With center h comma k and radius r. Meaning if I see anything of this form, I can know it's a circle. So if someone told you for example, what is, if I say x equals 2 plus 3 cosine theta, my y equals minus 1 plus 3 sine theta, for your theta going between 0 and 2 pi. Right? So if someone asks you that question, you can answer, oh, this is a circle. With the center is 2 comma minus 1, the radius is 3. And I can sketch that because I know how to sketch circles. They can also sort of change things on you a little bit. Let's say I gave you the same equation. And instead I told you theta goes from 0 to pi over 2. How does that change things? Right, it's just a quarter of that circle, right? So if I look at my circle, was my center 2 minus 1, so the center is here. If I created a new pair of axes that goes through there, and the radius is 3, so it'll just give me the arc here. Right, it'll just give me a quarter of that circle. But it's shifted. Okay. So by restricting the angle, they can tell you what part of the circle they care about. Basically. So those are just some common ones. So, let's see. Let's do something here. So let's say my x is x of t, my y is y of t, and t is given between a and b. This is a parametric curve. Which we can find by sometimes eliminating the parameter, sometimes by plotting points. I didn't show you the plot points, but I'll show you right now. You can think of the first point, the initial point, as being the first t value. So as the point x of a, comma y of a, and final point x of b, comma y of b. So I can plug in the first t value into these pair, I get a coordinate, I can plot that. Plug in the last t value into this pair, I get another coordinate, I can plot that. That will be your first and last point. And by the way, we can get other points. By plotting intermediate t values. So again, let's do an example. Go back to the original. Part 8, by plotting the points. Right, so this you'd kind of only resort to if you can't figure out what curve this is describing, but it should be clear that this is describing a parabola by plugging one into the other. But if you didn't know that, what you could do is you can go back to good old plotting points. Right, which in practice is not really something we would do, but in theory, this, I guess it's somewhat enlightening. So you just, because your x and your y is in terms of t, your t is going to be considered as the independent variable, so you can just plug in a few numbers, right? So it's like plug in minus 3, minus 2, minus 1, 0, 1, 2, 3. Right? And then individually, you would figure out what is the x when that is t, what is the y when that is t. And what you're doing here is you're creating coordinates. So this is sort of course, what you would obtain. It's coordinates on the graph. So I can say when t is minus 3, I plug in minus 3 here. That gives me minus 5. When t is minus 3, plug in there. That gives me positive 9. T is minus 2, plug it in here. That's minus 4 plus 1. It's minus 3. Minus 2, plug it in there. Get 4. T is minus 1, plug it in here. Get minus 1. Minus 1, plug it in there. Get 1. T is 0, plug it in there. Get 1. T is 0, plug it in there, and get 0, and so on and so forth. So that would be 3, that would be 5, that would be 7, and then this would just be 1, 4, 9. And so what that means is there are coordinates on this graph that you can plot now. This guy, this guy, this guy, this guy. Then you can go through on the graph and you can just start plotting those. You know, like 1 comma 0 would be on the graph. Then minus 1 comma 1 would be on the graph. Minus 3 comma 4 would be on the graph. Minus 5 comma 9 would be on the graph. Three comma 1 would be on the graph. 5 comma 4 would be on the graph. And 7 comma 9 would be on the graph. And you can see that when you plot that, you're getting that parabola that we knew was before. So if it's ever not clear, you can always just plot the points. In practice though, the curves I give you will be familiar curves. You wouldn't have to do this, but you could. Did you have a question?
Yeah, so in general, will you always be given like an AB bound, even if it's just from negative infinity to infinity, or sometimes is that just
Not always, it depends on the context.
If it's not given, do you assume it's just negative infinity to infinity basically?
If it's not given, you'll assume that
Or whatever
the
makes sense.
t would range over the domain of whatever, push it as far as possible, or as far as you need to solve whatever solution. So there's a point where if you want to know that something is a circle, you really don't need to go beyond 0 and 2 pi, because then all the points will just start repeating after that, and you're not getting any new information. Then you realize, oh yeah, it's just a circle. I can just fix that boundary to say, once you run through this, you would have achieved all points on this curve. Going outside of this interval, you're just going to achieve a point that we already know. So it depends on context. Many times you'll be given, many times you'll restrict it yourself because it just doesn't make sense to consider anything outside of it. But yeah.
Thank you.
So that's that. It's just a new way of thinking about how you do your typical curves. And you're sort of going along the route that you went through to invent trigonometry, where you just say, okay, here's a unit circle, let's pick a point and describe that point in terms of two new functions. We're doing exactly the same thing here, but now we want to do it with pretty much any curve, right? Give me a random curve, I'm going to find some two alternate functions to approximate each individual variable, and what can we get from that? And sometimes it will kind of be forced on you, but you in Calc 2, I'm pretty much going to tell you the rules pretty much all the time. So there are times when you want to try to, and sometimes you can even try to figure out a relationship between two quantities that you really don't know if they're related or how they're related, but you kind of do this statistical analysis kind of thing, you know, where you can realize, okay, I want to know if these two things have a relationship. So you measure them individually, right? Oh, I noticed this one is never negative. It never returns a negative value. And it's increasing like crazy. Let's pretend that it functions like e to the t, okay? This guy, sure, I can attain negative values, but in every interval of time, it increases by the same amount. Let's approximate this as a straight line. And so you can come up with two separate things that describe these two variables, and then you try to merge them, right? And you get a relationship between them. And then that leads you to further research. Let's see if this relationship is actually true. Now let's measure them together in sort of some, well, what was here before we got here, bivariate statistical data, and you can actually analyze whether these two things share the relationship that you guessed. And you can kind of tweak that relationship. So sometimes looking at a system in general is very complicated, but when you start isolating pieces of that system, finding functions that describe each piece, then it can kind of be easier to fit it all together and substitute one thing into another to kind of build up to the more complicated, broader system. So this is kind of useful both in hindsight and in foresight. It's a very useful technique to be able to isolate variables on their own. That being said, in this class, I'll always actually tell you what I want you to think of each variable as, or tell you the curve that I want you to parameterize, and you'll be able to do it. Let's move on to the calculus. we're going to talk about derivatives mostly here. So there's a formulation of the chain rule that says the following. It's not the one that people usually think about when they think the chain rule, but it's one way of writing down the chain rule. That dy dx can be equal to dy du times du dx. I don't know if you guys remember that version of the chain rule. But it's sort of like, let's say your y was f of x, right? Some function raised to the nth power, and you want to find the derivative. What some people started out doing was say, okay, call that inside just the function u, so I can think of my y as a function of u. And so now what happens is this guy is going to be the derivative that I'm going to multiply on the outside. So it's my dy dx, right? To find derivative with respect to x, ultimately I differentiate the outer function, and then I multiply by the derivative of the inner function, which is the du dx. So it's one way to think of the chain rule. It's not usually the way, but it's a mathematical way of expressing the chain rule as this guy. So we're just going to actually piggyback on that. Why? Because this rule introduces a new variable, which is what we want to do. And I wrote u there because that's usually how it's stated. But instead, use t, i.e. I can think of the derivative of y with respect to x as a derivative of y with respect to t times the derivative of t with respect to x. And this is something that will be hammered home in future classes, but the Leibniz notation of derivatives is very functional. You can treat it like fractions usually and do algebra with it. So the thing is, what we could do here is we could realize that this guy, I can flip and multiply and obtain this. Of course, provided we're not dividing by 0. Provided the derivative of x with respect to t is not equal to 0, we can actually do this. And so this is a form. This is how to find the first derivative. Of a curve if given parametrically. The derivative will also be given parametrically. The derivative will also be in terms of t. So this is when you don't want to eliminate the parameter, but you do want to find the derivative. But it's probably difficult for you to come up with a relationship that connects x and y. So what you do is you stay in the t universe and you do everything in terms of t's. And this is how you would get it done, just by kind of rewriting the chain rule in a convenient way. So let me show you an example of that. I actually did actually gave you the form for the second derivative first. Okay. Oh, my first example is a big example. I tell you a lot of things before. I'll tell you all this first, and then we'll do the examples next time. So I also tell you about the second derivative. the second derivative, and again we're going to use the Leibniz notation. Remember that that's kind of the notation for the second derivative. But what that is it's just the derivative of the first derivative Now this is going to seem kind of weird, but again, the Leibniz notation is very convenient, and it turns out we can use it this way, and then they prove in hindsight that this actually is mathematically valid to do. Which we're not going to prove it, but I'm just going to show you the trick. In the first derivative notation, divide by dt in the top and bottom. And then what you can get is that this is just d dt of this guy divided by the derivative of x with respect to t. So this guy we would find using this formula. It will be a function of t. We're going to differentiate that with t with respect to t again. Then I'm going to divide that answer by dx dt, and that will end up being the second derivative. I get it if manipulations like that seems weird to you, but it's actually totally valid. And when you get to differential equations, you'll do a lot more things like that. Like the notation is, the Leibniz notation is surprisingly very versatile notation. It's very functional notation. You can essentially think of it as a fraction in its own right. And also, again, something that's very important when we're talking about derivatives is tangent lines. This is pretty much the most important use of a derivative, is to find a tangent line. We know a tangent line is horizontal if we know that dy dx equals 0 at the point, right? So basically this would mean that dy dt over dx dt equals 0, which would mean your dy dt is equal to 0, but dx dt is not 0 at the same time. So as long as you're not dividing by 0 and the top of your fraction is 0, it is 0. So this gives you the horizontal tangent line. So find where your y derivative with respect to t is 0. Make sure your x derivative is not 0 at the same time, and that's where the points where you'll have a horizontal tangent line. Similarly, vertical tangent lines occur when you're undefined. And of course, we have to be continuous on some interval approaching these points to actually make this assumption, but I'm just saying the same thing. This would mean that your dx dt will hit 0 at some point, and that kind of messes up this derivative. That forces it to be undefined. will I do? Let's finish. Suppose if to determine dy dx, if both dy dt and dx dt are 0, right? That means you care about the point where dy dt over dx dt. Of course, you can't plug in 0, but they're approaching 0 over 0. How do you think you can sort of talk about what the derivative is doing? We can use limits with L'Hopital's rule to see what the derivative tends to. So let me write down the example I'm going to do. You guys can try it on your own, and we'll see on Tuesday. How you guys did. And on Tuesday, I also want the homework for work. So let's switch here. So here's an example. We'll do next time. So let x of t equals t squared minus t plus 2 of y of t equals t cubed minus 3t. A. Find dy dx. B. Find the second derivative. C. When is the slope 3? Find the equation of the tangent line. When t is equal to minus 2. So we'll stop there. We'll do that next time. I recommend that you try it on your own so that when we're going through it, it's more digestible. We'll finish up this section and talk about polar coordinates.
The homework on work is due on Tuesday.
Huh?
The homework on work.
Yeah, work is due on Tuesday. Do some work this week.